Nat 4-5 Physics, Acceleration. The key areas we will cover today are the definition of acceleration, calculating acceleration, and determining acceleration from an experiment. Acceleration. Acceleration is a quantity that describes how quickly the speed or velocity of an object changes. It is defined as the change in speed or velocity per unit time. We can see a triangle representing this. We've got change in speed at the top, acceleration at the bottom left, and then time at the bottom right. As an equation, the triangle becomes A equals, there's this triangle just here, which is a delta symbol, V, divided by t, where A is the acceleration measured in meters per second squared, delta V is the change in speed or velocity measured in meters per second, and t is the time for the change, measured in seconds. Example 1. The speed of a car changes by 10 meters per second in 5 seconds. Calculate the acceleration of the car. As always with equation-based questions, we want to write down what we know and what we want to find out. So we want to calculate the acceleration of the car in this question, so the question mark goes next to the A. Our change in speed, so delta V, is, we can see just here, 10 meters per second. And our time is, we can see up here, 5 seconds. Now we want to write our equation out. A equals delta V divided by t. And now we want to substitute in our values. So the acceleration equals the change in speed, which is 10, divided by our time, which is 5. So our acceleration is 2, and remember the unit for it, it's meters per second squared. Example 2. A plane accelerates from rest to 36 meters per second in 20 seconds. Calculate the acceleration of the plane. Again, the acceleration is what we want to work out. Our delta V, so the change in speed, we can see just here is 36 meters per second. And our time is 20 seconds. Notice that the sentence didn't specifically say the change in speed is 36 meters per second, but it said the plane accelerates from rest to 36 meters per second. From rest is another way of saying from a speed of 0 meters per second. And so we know the difference between 0 and 36 is 36, so that's why we have this number just here. Moving on to our equation, we know that A equals delta V divided by t. So A equals 36 divided by 20. Popping that into a calculator, that gets us to 1.8. So our acceleration equals 1.8, and remember your units again, meters per second squared. Example 3. A train travelling at 8 meters per second accelerates to 20 meters per second in 2 minutes. Calculate the acceleration of the train. Again, the acceleration is what we want to calculate. We need our change in speed and we need our time. We can see the time just here is 2 minutes, which you remember we always have to have time in seconds, so 2 multiplied by 60 is 120 seconds. And now let's have a little look at the change in speed. We're given two numbers here. Initially the train is travelling at 8 meters per second, and then it accelerates to 20 meters per second. So we need to find the difference between these values because it's the change in speed we want. So 20 take away 8 is equal to 12 meters per second. The train increases its speed by 12 meters per second. That's our change. Now that we have our change in speed and our time, we can calculate our acceleration. So A equals delta V over t. Our acceleration equals 12 divided by 120. Therefore, our acceleration is 0.1 meters per second squared. Example 4. A car accelerates at 3 meters per second squared for 4 seconds. Calculate the change in speed of the car. This time, it's not the acceleration we want to calculate because we're given that in the question, 3 meters per second squared. It's actually the change in speed we want to calculate here, and we are given the time, and that's 4 seconds. We can see that in the question. Using our equation, A equals delta V over t, we can substitute in our values. So 3 equals our change in speed over 4. Rearranging this, we want to bring the 4 up, so we want to multiply the 3 by the 4. So our change in speed equals 3 times 4, which gives us an answer of 12. And because it's a change in speed, that's measured in meters per second. Example 5. A racing car starting at rest accelerates at 5 meters per second squared and reaches a speed of 35 meters per second. Calculate the time taken to reach this speed. So this time it's the time that we're calculating. So putting down our values, we can put a question mark next to our time. Our acceleration comes from the question, that's just here, 5 meters per second squared. And our change in speed, if we have a look, the sentence has a key word that we looked at earlier. Did you spot it? It says starting at rest. And we can remember that starting at rest means the racing car is starting at 0 meters per second. And we can see that it reaches a speed of 35 meters per second. Therefore, we know that the change in speed is just 35 meters per second, because that's the difference between 0 and 35. Now that we have two of our values, we can calculate the time. So acceleration equals the change in speed divided by time. We can substitute in our numbers, so 5 equals 35 divided by t. We can either now use our triangle to help us figure out how to get to time, or we can work through this in a couple of lines. So what I like to do is take the time up to the other side by multiplying. So time times 5 equals 35, and then I'm going to carry on to the right hand side. We can get rid of our 5 by dividing it down onto the other side. So time equals 35 divided by 5. This gives us a final answer of 7 seconds. We can also refer back to our triangle when we're doing this. We know that the change in speed is on the top, the acceleration is on the left, and the time is on the right. If we cover up our time, we can see it's equal to our change in speed divided by our acceleration, which is exactly what we did just here. Either way, you're going to come out with the same answer, which is 7 seconds. What you could do now is copy and complete the following table for extra practice. Pause here if you'd like to do that. Now you can check your answers. To be able to carry out an acceleration experiment in the lab, you need to be able to measure the following 3 quantities: the initial speed, the final speed, and the time taken for this speed to change. An experimental setup for measuring acceleration is shown on the next slide. What we have just here is very similar to our setup for measuring instantaneous speed, but this time you can see that we have 2 light gates. What's going to happen is we're going to let the trolley with the card on it roll down the ramp, and it's going to go through the first light gate. When the front of the card goes through the light gate, it will stop the beam of light and the timer will start. And when the end of the card moves past the light gate, the light will be allowed to shine again and the timer will stop. The trolley will then go further down the slope, and the exact same thing will happen at light gate Y, with the timer turning on and off when the card moves through the light. The difference between these times is what we use for our differences in speed, as these times are used to calculate the instantaneous speeds at light gate X and light gate Y. We also have a ruler just here. Our ruler is for measuring the card on top of the trolley. As we know, we use this distance, this length of the card, as the distance in the instantaneous speed calculation. We also have a stop clock to measure the time the trolley takes to go from light gate X to light gate Y, so the time between these two, rather than the time individually. As a recap, let's think about each of the individual measurements. To get to the initial speed, we would measure the card with the ruler, and we would use light gate X and its timer to find the time that the trolley took to pass light gate X. We then carry out an instantaneous speed calculation. If you need a recap on instantaneous speed calculations, you can look a couple of lessons back and follow along there. Now we want to calculate the final speed. Again, we want to use a ruler to find the length of the card, and this time use light gate Y and its timer. We then carry out another instantaneous speed calculation. Finally, we need the time taken to change the speed. So we start the stop clock when the trolley reaches X and stop the stop clock when the trolley reaches Y. A possible set of data from the experiment is shown below. The length of the card could be 0.048 meters, and the time for the card to pass through the light gate X could be 0.012 seconds. The time for the card to pass through light gate Y would be 0.01 seconds. And finally, the time for the trolley to travel between light gate X and light gate Y could be 0.4 seconds. What we want to do is show that for this data, the acceleration of the trolley is 2 meters per second squared. Let's calculate the initial speed, the final speed, and finally the acceleration to see if it really is 2 meters per second squared. Here are the values we were given on the previous slide. First of all, let's calculate the initial speed. We know that to calculate instantaneous speed, which is what this initial speed is, we need to take the length of the card and divide it by the time that the trolley took to pass the light gate. For the initial speed, this is the time at light gate X. So the initial speed is equal to the length of card, so 0.048 meters, divided by the time to pass light gate X, so that's 0.012 seconds. Popping this into a calculator, we get to a speed of 4 meters per second. Let's do the same thing for the final speed. The length of the card is still the same, so 0.048, but this time it's the time taken to pass light gate Y, so this is 0.048 divided by 0.01. Popping this into a calculator, what we get to is 4.8 meters per second. Now that we have the initial speed and the final speed, we can go on to working out the acceleration. We know that our acceleration equation is a equals delta v divided by t. First of all, let's work out what delta v is. That's going to be the final speed take away the initial speed, because that's our change in speed. So 4.8 take away 4, that's 0.8 meters per second. And this time, the time is going to be the time that the trolley took to travel between light gate X and light gate Y, so 0.4 seconds. We can use our equation, A equals delta V over T, and substitute in our values, so 0.8 divided by 0.4. What we get if we do 0.8 divided by 0.4 is 2, and that's exactly the number we were meant to come up with, 2 meters per second squared. As well as writing our equation A equals delta V over T, we can also write the acceleration equation as follows. A equals V take away U divided by T, where A is our acceleration measured in meters per second squared, just like before. V is our final speed measured in meters per second. U is our initial speed measured in meters per second, and T is the time for the change measured in seconds. So all we've done here is split up our change in speed to the initial speed and the final speed. Example 1. When overtaking a bus, a car increases its speed from 9 meters per second to 21 meters per second in a time of 4 seconds. Calculate the acceleration of the car. So we know we're calculating acceleration, so that's where our question mark goes. The initial speed, so U, we can see in the question, if the car is increasing its speed from 9 meters per second, that's going to be our initial speed. And it's increasing it to 21 meters per second. So that's our final speed. And that's in a time of 4 seconds, so that must be our time there. Now that we have our three values, we can go on to calculate our acceleration using our equation. So A equals V take U divided by T. Popping in our numbers, we get 21 take away 9 divided by 4. 21 take away 9 is equal to 12, so you can do the top part of your equation first if you would like, or you can put the whole thing into a calculator if you feel confident with doing that. What we get is 12 divided by 4, which is equal to 3, and that's in meters per second squared. Example 2. A student starting from rest reaches a speed of 5.1 meters per second when they are chasing another student in the corridor. Calculate the acceleration of the student if the chase lasts for 3 seconds. Again, it's the acceleration that we're calculating, and we need the initial speed, the final speed, and the time. Looking at the question, similar to earlier today, there is a key word here that we're noticing. The key word is starting from rest, that word rest there. And remembering back to previously, that means that the student is starting from a speed of 0 meters per second. So that's going to be our initial speed. U is 0 meters per second. Our final speed, we can see, is 5.1 meters per second. And our time is 3 seconds. We can now use our equation, A equals V take U over T, and pop in our numbers. So our acceleration is 5.1 take away 0 over 3. What you can notice here is the top of our line. If we've got 5.1 take away 0, that is just 5.1. So we can simplify this to 5.1 divided by 3, and 5.1 divided by 3 is equal to 1.7. So our acceleration is 1.7, and don't forget your units, that's meters per second squared. Example 3. A cyclist travelling at 7.7 meters per second applies the brakes and comes to a rest in a time of 3.5 seconds. Calculate the acceleration of the cyclist. So again, we're calculating the acceleration. We need the initial speed, the final speed, and the time. Having a look in our question, the cyclist is initially travelling at 7.7 meters per second, so that's our initial speed. And we can see that magic word again in here, comes to rest. So they're applying the brakes and coming to a rest, so that's 0 meters per second, which is our final speed, and that's in a time of 3.5 seconds. Now we can put the numbers into our equation. So first of all, A equals V take away U divided by T. So A equals our final speed of 0, take away our initial speed of 7.7, divided by our time of 3.5. In our previous example, it was a number take away 0, which just leaves us with the original number, whereas here we have 0 take away 7.7. This means we cannot ignore this minus sign in the middle. We have to keep on to that. So, in our next line of working, we can simplify this to acceleration equals negative 7.7 divided by 3.5. Negative 7.7 divided by 3.5 gives us an answer of minus 2.2, so we still need to keep that negative in there. And again, that's in meters per second squared. This minus is in there is showing us that instead of accelerating, the cyclist is decelerating. And we know this because they're applying brakes and coming to a rest. They are slowing down. So I'm going to add that in just here. This little minus sign means they are slowing down. It shows a deceleration. And if you don't have a negative sign, that means your number is positive, which shows an acceleration, which was seen in previous examples. Example 4. A jet aircraft accelerates from rest at 7.5 meters per second squared for 8 seconds. Calculate the final speed of the aircraft. So it's not acceleration we're calculating this time, it's final speed. So A, U, V, and T. If it's the final speed we're calculating, V equals our question mark. Looking at our question, the aircraft accelerates from rest. That's our key word there again. From rest means we are starting at 0 meters per second. And they're accelerating at 7.5 meters per second squared. And they're doing this in a time of 8 seconds. Now, if we use our equation, we've got A equals V take away U all divided by T. We can pop our numbers in. So 7.5 equals V take away 0 divided by 8. We can simplify this for ourselves and realize that V take away 0 is just V, so we can write this as 7.5 equals V divided by 8. And now to get v by itself, we want to multiply the 8 up onto the other side. So I'm going to carry along the right-hand side here. V equals 7.5 multiplied by 8, and this gives us an answer of 60. And remember, because that's a speed we're calculating this time and not acceleration, it's just going to be meters per second. Example 5. A rocket accelerates at 9 meters per second squared and changes its speed from 376 meters per second to 592 meters per second. Calculate the time taken for this change in speed. So this time we are calculating the time. So we've got A, U, V and T. Our question mark is going next to the T. Having a look in the question, the rocket accelerates at 9 meters per second squared. And we can see that it changes its speed from 376 to 592 meters per second. So our initial speed is that 376, and the final speed is 592, both in meters per second. Let's take our equation, A equals B take away U divided by T, and pop in our numbers. So 9 equals 592 take away 376, all divided by the time. Let's simplify this to make things easier for ourselves and do 592 take away 376 first. That's equal to 216. So 9 equals 216 divided by our time. Now we can either use our equation triangle or take a couple of lines to take the time to the top of the equation. So first of all, we want to multiply the time up to the other side. So 9 times time equals 216, and then we want to take the 9 to the other side by dividing. So time equals 216 divided by 9. 216 divided by 9 is equal to 24, so that's our final answer. Time equals 24 seconds. What you can do now for extra practice is copy and complete the following table. Pause here if you need to take time to do so. Here is the completed table for you to check your answers.